Hello everyone, I hope all you are fine. Let's check it out what we have done so far, especially in the last session. In the last session we have studied on synchronous machine part 2, that is the second slides, and then we have completed a current circuit of cylindrical rotor synchronous machine, and then it was something here. Since machine is symmetrical, we only need to represent one phase of the machine. That is the equivalent circuit representing only one phase armature winding. That's enough. Okay, and then those are the equations for generator operation and motor operation. Let me draw this equivalent circuit and rewrite the equation. Here is the equivalent circuit. EF, armature reaction reactance, armature leakage reactance, and then armature winding resistance, and that is the terminal voltage. Let me show some more terms. If current is outgoing from the positive terminal, that is generator operation. If current is into the machine through positive terminal, at that time machine will operate in motor mode, motor operation. Okay. The terminals here we can say U and X, that is the one phase winding. Remember, UX, VW, VY, and WZ. Those are the terminal labels belonging three-phase armature winding in old terminology. In newer terminology, especially getting famous around European countries, U1 and U2, V1 and V2, and W1 and W2. Those are new terminology, new labels, but the purple one are old labels. Okay, UNX, old but still used. Okay, let's write Kirchhoff voltage law for generator operation. Kirchhoff voltage law around the loop, KVL. Induced EMF in the armature will be equal to current times JXA plus current times JX sigma plus current times RA plus V1. Here are something missed, gentlemen and lady. Take care. All those voltages and currents are in phasor representation, having some magnitude and phase angle with respect to reference. And do not forget J with reactances. Here are J. So let me arrange the equation for a better understanding. V1 plus current array plus Ji x sigma plus Ji x A. That is a new arrangement. I arranged this equation like this on purpose because this style will help you draw a better phasor diagram, a meaningful phasor diagram. That sequence is helps us. Okay, that is the equations defining generator operation. Generator operation. Those are the equations. That is just enough. That one is just enough to define generator operation. Okay, let's write another Kirchhoff voltage law around this direction. Beep beep. The same one, of course. KVL for motor operation. In fact, it doesn't matter the green loop or blue loop you use. What important is the current's direction. Ladies and gentlemen, take care. In motor operation, current direction will reverse with respect to generator's mode. Current goes to minus I1 in comparison with generator's direction. Current changes its direction in motor mode. In motor mode, you apply some electrical power, you convert it into mechanical power on this device. That is the device converting energy converting device. Energy conversion occurs on this device. Okay. Now, having this equation, substitute negative current V1 minus current array minus Ji x sigma minus Ji x A EF. That is the equation for generator motor operation. Do not forget voltages and currents. They must be in phasor representation. Do not forget J's together with reactances. Okay, let me make a better view arrangement. Applied voltage will be equal to EF plus current array plus Ji I1 x sigma plus Ji I1 x A. Phasor, J together with reactance Ji phasor. That is the final equation after arrangement. That is the equation defining motor operation. Okay, ladies and gentlemen, as you have seen, by having equivalent circuit, by applying Kirchhoff's voltage law and some small definitions, you have find out equations. But here is something shortened. XS means XA plus X sigma. That is called as synchronous reactance. Synchronous reactance. Of course, you can abbreviate those parts. XS equal to XA plus X sigma. That is called as synchronous reactance. That is armature reaction reactance. That is armature leakage reactance. And you can also make it more compact. RA plus JXS plus V1 EF. That is a more compact writing. But I prefer this one. Sometimes this one. But I like this one. Because this helps us to understand phasor diagrams better. Okay, some more definitions. Here is a voltage drop on this element, J current XA. That is the voltage drop on this element. It is called as armature reaction EMF. Armature reaction EMF. And after these, in fact, in generator mode, for example, you have induced electromotive force. You convert mechanical energy into electric energy across this device. But that is the no-load voltage or voltage EMF induced by rotor magnetic field. And then, in case there is a current supplied to a load, here would be some voltage change on this device. This device is called as armature reaction reactance, and the voltage across this element is called as armature reaction EMF. And then after armature reaction effect, here's E. All those are phasors. E. And let's define what those three are. EF, EMF induced in armature due to rotor field, main field. Sometimes it is called as no load voltage. Sometimes it is called as open circuit voltage. Okay, what does it mean? Here you see what is the voltage across the terminal. Here is the voltage. You can take this out. Voltage is equal to EF minus current array minus JI1 X sigma minus JX I1 XA. That is the voltage on the terminal. But in case there is no load, in no load case or open circuit case, there is no current. In case there is no current, there is no voltage change on these those three elements, so no load voltage will be equal to induced EMF in the armature. That means all those three have the same meaning, and we call induced EMF EF, armature EMF, in one phase winding. And then EA, that is called as armature reaction EMF. It is equal to J I1 X sigma BB XA. You know what EF is? EF is 444 times maximum flux, frequency, number of turns in armature, and winding factor of the armature. That is the EF. Induced in the across the armature winding. Okay. And then there was another element which is E here. Okay, let's define it. E, load, EMF under load, EMF under load, or after loading, under load. What does it mean? In the beginning you have induced such an EMF, and then after supplying some loads, here's a voltage change due to armature reaction. There will be strong increase, dramatic increase, or dramatic decrease, you know. And then here is a load EMF. That is called as EMF under load, under loaded condition, blah blah. EMF, load EMF. All those are phasors or something, vectors. Okay. You know the terminal voltage V1 and I1, terminal parameters. V1 and I1 are terminal parameters. One is terminal voltage, the other is terminal current. Okay. And as a new topic today, we draw phasor diagrams defining rotor, generator and motor operations. Okay, it will be more clear in Turkish text, but I will lecture all of them. Okay, phasor diagrams. For phasor diagrams, for round rotor synchronous generator. I mean generator operation. Okay, first generator, and then I will study on ohmic, pure ohmic generator. Okay, ladies and gentlemen, assume that here's a generator, synchronous generator having three phase. Here's an excitation coil, and you have applied some field current, and here's a shaft, and it is driven by a prime mover. You have applied some mechanical input here in terms of torque and angular speed. Mechanical, okay. It is also equal to synchronous speed. And then that power, mechanical power, will be converted into electric power. And here would be some load. Let's say load. But load in a generator will be pure ohmic, having a power factor of unity, or load would be lagging current or inductive, having a power factor which is less than less than unity. And another case, a load having leading current, which is capacitive load, and then again power factor is less than unity. But phase angle is negative here in lagging load. Phase angle is positive here in leading load. Okay. Phase angle is 0 in pure ohmic operation. There will be 3 different operating cases for generator mode. Yes. How can we draw phasor diagram? Phasor diagrams realize a schematic representation of a complex equation. Okay, let's remember the complex equation for generator's operation, which is EF is equal to V1 plus current times RA, J current X sigma, J current XA. Phasor, J due to reactances, current phasor, voltage, EF. Okay, ladies and gentlemen, left hand side must be equal to right hand side. Real parts must be equal to real parts of the right hand side. Imaginary parts of left hand side of the equation must be equal to imaginary part of the right hand side of the equation. And a complex equation has 2 scalar equation. Now, some of them are some parameters are easy to measure. Some of the parameters are easy to measure. For example, the easiest one, terminal voltage, current, and the phase angle between those two. Phase angle, power angle between those two phasors, those two parameters. That is phi. Those are voltage and current. Let's say magnitudes. By using a voltmeter, we can only define the amplitude. Remember, excuse me, V1. That is the just magnitude, RMS value, or magnitude, amplitude, genlik. But if I say I1 phasor, that means there is a magnitude and an angle. Beep beep. That is the angle. That is the angle of current with respect to reference, which is voltage. Now, any parameter on this equation will be defined with respect to as a reference. With respect to reference, voltage vector is chosen for as a reference. It means the angle of voltage is 0. It is just on the reference line. Okay, then current's location is measured with respect to voltage, which is reference, and it is phi. Phi is the angle from voltage to current. Phi is the angle from voltage from reference to current. And then easiest one was the I1, V1 and phi. Some of them are not easy, but can be found by applying some special procedure or some by using some experimental results. For example, RA, X sigma, XA can be found out by conducting some special experiments. RA, X sigma, XA can be found experimentally. Okay. What about the EF? Beep, beep. EF and its angle. EF and its angle delta. I mean EF as a phasor. It has a magnitude and an angle with respect to reference. Delta is the angle from reference to EF. Delta is called as load angle. In some book it's also called as torque angle. I prefer load angle. Okay, and that is the most difficult one. It is the most difficult parameters. Let me say parameters. Those are, I mean EF and delta. Those are the most difficult parameters to find out. Most difficult one. It needs some estimation or conducting some calculations. Okay, let's repeat the equation. First of all, let me talk about some complex representation. We show or represent phasor by dot. That is the RMS phasor. It means that is phasoral representation. And then any complex number can also be represented by EF and delta. That is polar representation. And then some complex numbers can also be represented by EF times e to the j delta. That is Euler's representation. We generally don't use this, but we like this. We like also this. And there's a third one, which is Cartesian representation. Let me say EF real part plus J EF imaginary part. It looks like A plus JB. That is Cartesian representation. Okay, for example, remember the Cartesian term here in the abstraction here. Ra plus JXS. That is a complex number. Looks like, let me say Ra, change color first. Ra plus JXS. That is Cartesian. Okay. Let's write this guy in terms of polar representation. Let me first define Z. Z is equal to R squared plus XS squared in square root. That is the magnitude of Z, and the Z phasor can be written like this: Z amplitude times angle. Let's say theta. Theta is equal to arctangent of XS over Ra. That is the angle theta. That is the angle of impedance. Impedance angle of rounded or synchronous machine. Okay, sometimes we prefer Cartesian representation, sometimes we prefer polar representation. If you use old-fashioned, old-school calculators, you'd better use Cartesian representation. That is the fundamental one. But if you have some more high-level calculators, so you can use any of top three. If you use paper and pencil, that will be better to use Cartesian representation. Okay, now what we have done so far. We are about to draw phasor diagrams, and we have defined the reference, which is V1, and then we define all other vectors or phasors with respect to reference, and then our aim is realizing the equation for the operation. Now we deal with generator operation first. So let's realize these equation by using individual phasors. Okay, and Hoca said current would be pure ohmic, inductive and capacitive. So let's start with ohmic operation. A ohmic generator, ohmic let me say ohmic loaded generator. I mean phase displacement is 0. Okay, first of all, take care what I am doing. First, I draw a reference line. That is the reference line. Now, in Turkish written book, in early books, we have chosen reference line vertically because you know, books are in portrait mode, and it is easy to complete a phasor diagram in portrait mode. So reference is generally chosen in vertical direction, but it is a bit confusing because reference generally represents real axis in phasors, and quadrature axis is generally represents imaginary axis. So in mathematics, you know, x-axis is real and the y-axis represents the imaginary axis. So it will that representation will be a bit confusing. So in recent years, I generally prefer the approach used in mathematics. Okay, that is the reference, and that is the reference rotation, which is in counterclockwise direction. Okay, here it is also in counterclockwise direction. That is the positive rotation direction. It is universal approach. Vectors, phasors are always rotate in counterclockwise direction positively. That is the positive direction of vectors. Then I have chosen V1 as a reference, and then I draw V1 in line with or parallel or on reference line. Remember, EF is equal to V1 plus I1 RA J I1 X sigma plus J I1 XA. That is the equation we want to satisfy. And that term is already drawn in line with reference line. Okay. Let's talk about current. Here's the current. Okay. Current must be ohmic. Ta-ta. Here's the phase angle. Let me show it down here. Phase angle is 0 because it is supplying pure ohmic loads. And then that is the vector times scalar. Current times scalar makes a new vector in the direction of current. Scalar array makes no change in the direction of the new resultant vector, which is I1 times array. It is a tiny vector because we experimentally know that XA is the largest element in the parameters here shown. X sigma is the second one, array is the smallest one. The relation looks like this. As a just example, the size of the XA, if it was 10, X sigma will be 1, and this guy will be 0.01 or 0.1. That is negligibly small. We generally neglect or omit it. Array is very small resistance. Okay, but the dominant one is this. That is very dominant. So, while you are driving, please take care those relations. The term coming from XA must be the largest one. Okay, let's come to the second one. Current times X sigma. Okay, current is here. Current times X sigma must be larger than this guy. Yes, current times X sigma. But, Houston, here is J. J causes a vector to rotate in 90 degrees in clockwise direction. J I1 X sigma. Take care. J causes 90 degrees leading movement. I mean, let's say here's the real axis, here is imaginary axis. On these axes, just imagine here's 3. When you multiply 3 by J, ta-ta, it would be here. You see a 90-degree leading representation. J causes a vector to lead 90 degrees, to go ahead 90 degrees. Okay, let me show you here. Blue one, blue one, blue one. So, must be larger than the previous one. J times I1 X sigma. And the largest guy, this guy, come in. Current times XA, the largest one, somewhere here, let me say JI1 XA. As you have seen, Houston, you have added all those 4 elements to each other. I have started with V1 and then I have added this guy, then this, and finally this guy. All those terms summed together and we got E1. Ta-ta, Houston, Houston, here's E1, a new vector, resultant vector. Hoca said that was the most difficult one to measure, to obtain. EF vector. The angle of EF is the angle between voltage and EF. That is called as delta. Delta, you start from V, which is the reference, and try to find out EF, and you sweep in positive rotation direction. So delta is positive. Delta is less than 90, of course. When delta reaches 90 degree, you know, machine go under pull out, machine will be out of synchronization. So that is the EF. And Houston, there is one more term which is E. Here it is. This term called as low TMF, and here's another one which is armature reaction EMF. Ladies and gentlemen, take care. In the beginning, when there is no load, we have induced or converted such an EMF and magnitude. And then after having some ohmic load, the amplitude of the induced EMF after armature reaction will be E. That is low TMF, that is no low TMF. And then the relation between those two is, under loaded case, the magnitude of the EMF has decreased. You see, E is the smallest one, smaller than the EF. Okay, that means armature reaction, which is this term, caused a drop or decrease. I said in the previous topic we had a topic armature reaction, and we had a tablature at the end of the course. I have summarized the armature reaction effects. In that tablature I called these events as slight decrease, slight decrease. In Turkish I say az köstek. Az köstek. Burada düşürücü bir etki yapıyor. Yükseltici etkiye Türkçe'de destek diyorum. Az düşüşlere de strong slight demiştik. Çok kösteklere de birazdan dramatik sıfatını kullanacağım. Bir tane daha yapayım, ondan sonra ara yapayım. And now, that was the ohmic loaded generator operation. Now let's continue with inductive motor operation, inductive generator operation. B. Inductive generator operation. In such an operation, phase angle will be negative or lagging. Lagging. Okay. First of all, again, as usual, draw a reference line. Choose a reference rotation which is always in counterclockwise direction. And then, by using phasor relations, try to realize the generator's equation, which is written here. That is the generator's equation. Now, let me write voltage, because I have chosen voltage phasor as a reference. Voltage as a reference. The angle is 0, that means it is on the reference. On the reference line. Okay. And then I will define all other phasors with respect to reference. Now, Houston, current is lagging. Current is lagging in inductive generator operation or inductive operation. Here's the current, but try to find out where the current is. You should move in negative rotation direction. That is the positive direction. Since the angle is negative, you sweep in negative rotation direction to find out the current's position. That is the inductive current. Phase angle phi is negative right now. That means inductive loading. And we also call this as lagging, geri kalan, lagging current in inductive loads. And then continue to realize the equation. That is the current times Ra. Ra is a smallest scalar. Ra times I1 makes a new beep beep beep. I'm sorry, it is wrong. It must be in the direction of I1. That's it. I1 in the same direction, scaled by a scalar, which is Ra. the smallest guy. And then the second voltage drop on this element by 90 degrees leading due to J, that is J times current times X sigma. Those are perpendicular to each other due to J. And then the final element, which is armature reaction element, the largest one, JI1 armature reaction, XA. Houston, we have added all those voltage drops together to find out where the EF is. And I have found out the EF finally. That is EF. EF phasor. The position of EMF from voltage to EF, which is delta. Delta is positive, as you see. If delta is positive, that means machine is operated as a generator. Okay, let's say generator's operation. If it is negative in the future, it means a machine is operated as a motor. Now, delta is positive, so machine is operated as a generator. Ladies and gentlemen, here's a low EMF between those two. Low EMF. And that is armature reaction EMF. In the beginning, you have induced EF in magnitude, and then after armature reaction on this element, after armature reaction, there is low EMF in magnitude. You observe that low EMF is far more smaller than no low EMF. That means armature reaction causes a dramatic decrease in EMF, in voltage. In fact, in the beginning, we were talking about, in the previous courses, we have talked about that there were some FF, and then I'm not sure, yes, I remembered. There is an armature reaction MMF, and then those two MMF interacts each other to have such a resultant F. Now, gentlemen, FF over reluctance cause field, let's say Phi, and then EF 444 Phi blah 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 blah, that induces electromotive force of EF. That guy will induce EF somewhere here. Let me say, just scale. This guy induce EF, these guys induce armature reaction EMF, and that is the low EMF after armature reaction, resultant EMF. In the previous topic, we examine on MMF vectors or phasors. But now we deal with voltage phasors, current phasors. And again, we observe some armature reaction effects. As you see, there's a dramatic decrease. Dramatic means there is a drop in D axis, in these axis. Let me show the previous one. There is not much drop in D axis due to this guy. That is the dominant one. Remember how dominant it is. let me show. Where is it? Must be somewhere here. Houston, I'm sorry about that. Yes, here it is. That is the dominant one. XA, and XA cause a dominant voltage change, which is armature reaction EMF. That guy is the dominant one. And now here you see that guy doesn't have any drop on voltage axis, but in the inductive load case, you see, Houston, there is a direct axis component of armature reaction, and that causes dramatic effect. In case there is no d-axis component, we call slight decrease. Slight changes, decreases, are always in ohmic mode. Remember, always in ohmic mode. It doesn't matter whether the machine is operated as a generator or motor. Armature reaction effects always appear in slight decrease in pure ohmic loading case. Okay, we have completed those two, but let me show this guy on equivalent circuit again. Here's the equivalent circuit. Okay, load EMF is equal to EF minus armature reaction EMF in vectors, in phasors, for generator mode. Because here's a tiny KVL. This KVL says that induced EMF is equal to voltages around that tiny loop, which is current JXA, which is armature EMF, plus E. Now, if you take this out to left, it is equal to EF minus E. That is the load EMF. For generator mode, of course, in motor mode it would be a bit different. This guy will change its direction due to current. Current will change, so this term will change polarity in motor mode. Okay, always draw phasor diagram, use key KVL to write down the equations. Yes, we have completed inductive generator operation, and then let's continue on capacitive generator operation. That means phase angle is positive. In inductive operation, phase angle was negative, and here is in capacitive mode, phase angle is positive. We call leading current operation. Leading current operation. Okay, again, method is the same. First of all, let's draw your reference line and then reference rotation direction, which is always in counterclockwise direction, and then by using individual phasor elements, try to realize the equation satisfying the generator's operation. I1 x sigma plus J I1 xa. That is the generator's operation. By using individual voltage and currents elements and products, try to satisfy this equation and try to find out the most difficult parameters, which are EF in terms of amplitude and the position of EMF, which is lot angle. Okay, let's start with reference vector, which is V1. It is always on reference line. Here it is, V1. And then the current is leading. Start from reference and move in positive rotation direction because phase angle is positive. And then you have find out the current's position. That is phi. Phi is positive or leading, and it means capacitive property, capacitive current, capacitive loading. And then try to satisfy the equation current times Ra. That is a vector in the direction of current in very small length, because array is negligibly small. I1 times array. Array is very small, negligibly small. And then try to find out this guy, which is perpendicular due to J to the first one. That is perpendicular to current's position. J I1 x sigma. In fact, that is I1 x sigma, and that is J I1 x sigma. Those are perpendicular to each other. Yes, those are perpendicular, J I1 x sigma. And the final term, which is J I1 xa, is the largest one, dominant one, will be somewhere here. In reality, those are not so large, but I exaggerate to make them easily visible. For example, in reality, let's say here is 150 kilovolts, and here is only 100 volts, or let's say here is 800 volts. So you see the relation. The voltage will be 150 kilovolts. The other vectors will be very smaller in comparison with the reference. So, but in here, I should draw as readable as possible. So I draw them larger. Excuse me. I draw them larger, as if they are. And then, that is the last term I have added. Here I have summed all those 4 vectors. Finally, I have find out this guy. From origin to final position, that is EF vector. From reference to EF vector, there is a lot angle. As you see, lot angle is positive. Positive means machine is operated as a generator. And then the vector here is low TMF, and that is armature reaction. As you see, in the generator mode, first of all, we have induced EF in magnitude, some magnitude, and then after loading, load causes some armature reaction, and then after loading you have got these EMF. As you see, the sign, that is the greater than, load EMF is greater than the no load EMF, and armature reaction cause armature reaction cause a dramatic increase in EMF or E. E is increasing here in this example, in the capacitive operation. E is increasing. Strong or dramatic increase in capacitive generator operation due to armature reaction. Now, ladies and gentlemen, we have completed the phasor diagrams for round rotor generator operation. Here is the ohmic generator from the textbook in Turkish. Here's something wrong. That guy must be opposite FA, and then those are not important here, but let me show only for one diagram. EF, FF, EF and FF, those are perpendicular because EF, the relation between phi m or phi f have the same meaning. There is a perpendicular relation due to Faraday's law. Remember, n d phi over dt. Here EMF is perpendicular to flux in sinusoidal systems. If this is sinusoid, that would be cosine. If this is cosine, in function of cosine, that would be in the function of sine. So those are always perpendicular. And another relation can be seen here. Load EMF is perpendicular to resultant F. Load EMF is perpendicular to resultant F. No load EMF is perpendicular to rotor field, and armature reaction is perpendicular to FA. But here's something wrong. It must be downward in direction. We deal with MMF vectors and armature reaction in some previous topics called armature reaction, and but the same armature reaction effects will be observed in those phasor diagrams, so we catch the relation. There is armature reaction effect appeared in phasor diagram, so we make a connection. Again, this guy must be in opposite direction, but if I say you, please draw phasor diagram of inductive generator, you should draw such a relation, such a diagram, or this guy, voltage, inductive current, I times R, J I x sigma, J I x A, and then finally EF. And that is the positive delta, meaning generator's operation. Okay, here's one more angle I have forgotten to say. which is psi. Psi is inner power angle. Inner power angle. Psi is the angle being measured from EF to current. That is a special angle. It is drawn with a between a special two parameter, not for with respect to reference. It is drawn from EF to current. Let me show you. Where is psi? Psi is the angle from voltage to current. That is the psi. And here you see psi is negative. Psi is the angle between EF and current vectors. And then let me show you psi again. From voltage EMF to current, that is psi. Again, psi is the angle between EF and current phasors, inner power angle. And here is psi. It is not so clear, but here is the psi. From EF to current, that is psi. Psi is the angle between EF to current. Start from EF, move towards to current. Here you see, let me show you. Starts from EF, move towards to current to find out, and then that is the angle, psi, inner power angle. Now, ladies and gentlemen, we have completed generators mode phasor diagrams for three different operating cases, which are pure ohmic, some inductive, and some capacitive loading. Of course, someone can also draw pure inductive or pure capacitive cases. It's up to you. Okay, let's continue on motor operation. Phasor diagrams in English text. We first started here, and then those are the phasor diagrams in English slides. Here is the pure ohmic case. Some inductive or lagging current, inductive load, some capacitive load, I say some, perhaps I hope you understand. If phi is larger than 0, I mean phi is a leading current, a leading angle, but less than 90 degrees between those two, I call some capacitive. But if phi is equal to, if phi is equal to 90 or positive 90 degrees, that means pure capacitive loading. Or phi is negative 90, that means pure inductive. Phi will be minus 90 degrees. In such a case, we call pure inductive loading. Also, you can draw phasor diagrams to show armature reaction effects and to show or observe the relations. I will, at the end of the course, I will show you a flash animation to observe some displacements, some loci root of vector, it is root, how can I write root? Of vectors. Yer eğrisi, yani vektörlerin yörüngelerin demek loci. Vektörlerin yörüngeleri. Böyle bir şeyi tahmin eder hale geleceğiz. Loci, bazen bu Latinceden geliyor sanıyorum. Locus diye de söyleniyor. Loci, locus. Muhtemelen bir tanesi tekil, üstteki çoğul olabilir. Yani şimdi tam Latince etimolojisini bilmiyorum. Yes, we are about to start motor operation. And here is the animation we will deal with. And there is no motor operation phasor diagrams, but you are responsible. Let me write it down here. Motor, you are responsible with the motor operations phasor diagrams. Okay, take care. I draw them here. Phasor diagrams for round rotor synchronous motor or round rotor synchronous machine, especially in motor operation. Okay, it doesn't matter because the machine is the same. In fact, you got the machine. The same machine can be operated in motor or generator. Now we examine the same machine in motoring mode, in motor operation. First, let's cut a synchronous machine. For example, I hope I will find a good example. Let's say that is the armature. You see, when you cut the armature, you see some windings made of copper wires. And such windings, you remember, have some resistances, which is Ra, some inductances, totally Ls, causing excess, which is equal to Xa plus X sigma or La plus L sigma, which is leakage inductance, armature reaction inductance, synchronous inductance, and it is synchronous reactance, armature reaction reactance, and armature leakage reactance. Leakage. Kaçak. And then you in motor operation you apply some electric power. Let's say here's the network, Turkish National Grid, and then you apply some three-phase power, and then your aim is converting electric power into mechanical power. You use a motor or a machine acting like a motor. converting electric power into mechanical power. That is motor operation. And now, gentlemen, here is the network, connected some resistances and some reactances. It looks like a lagging current system. A lagging current, inductive system. Okay, let's start with a inductive motor or a lagging current motor. Inductive motor or lagging current motor. Okay, lagging current motor. That means phase angle is negative. That means a lagging current. And then you should satisfy the equation for motor. Motor's equation can be written as voltage is equal to EF plus current blah 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 ED. And then you know that is the most difficult one to find out. So let me take it out. EF is equal to V1 minus I1 array minus JI1 x sigma minus JI1 xa. Here is the equation to satisfy motor operation, and especially to define where EF is. Okay, let's start with reference. V1 chosen as a reference. As usual. We generally choose reference V1, but it is not God's law. It depends you. Sometimes choosing current as a reference will be easier, but not undergraduate courses. Generally, in graduate or master's degree courses, sometimes it would be easier to choose current as a reference. Sometimes. But it doesn't matter what you choose. It doesn't matter. The result is always okay if you say I choose blah blah as reference. The result will be the same in magnitude, but the result will be different in phase angle because you define some vector to another. Okay, let's draw the frame first. Let's draw the frame first. Here's the reference line. Here's the reference rotation, which is always in counterclockwise direction in mathematics, in physics. Then start from reference line in line with V1. V1 is in line with reference line. In line with paralel, üstünde anlamına geliyor. And then inductive motor operation, current must be lagging. Okay, draw current. Let me draw the current which is lagging. Start from reference, move in negative rotation direction to find out where the current is. That is the angle of displacement of current, which is negative right now. That means lagging current or inductive current, because you know inductive current causes some lagging current. Inductive loads cause lagging current. And then Houston, you should realize these equation. I1 array, yes, do it. That is I1 times array, I1 times array. That is the scalar element array, which is negligibly smallest one. So this guy must be subtracted. Tata. If I draw like this, I would add the vector. Now I subtract. This is all. That is right, or that is right. All those are right, correct. That is current times array, and then Houston. Let me make clear here, and then define current times array here, and then Houston, this guy, Ji1 x sigma, beep beep. That is the direction of I1. That is the direction of I1. Direction of the angle, the position which is perpendicular to original I1. Now, gentlemen, that is I1 J x sigma, a little larger than the previous one, and the final one is the largest one. Let me say somewhere here, that is Ji1 xa, which is armature reaction EMF, and then finally you have find out EF. The angle between voltage and EF is delta. Delta is negative. Motor mode. Now, if delta is positive, it is generating. If delta is negative, it is motoring. It produces mechanical output. Now, here's one more angle term, which is E. E is load EMF. Here's psi from EMF to current, which is psi. Now let's examine it. It is not clear in this sketch. In inductive generator operation, let me choose this guy. Here you see, in the beginning we have induced such an EMF in armature winding. Here's the armature reaction EMF due to load current or current in the armature, and then that is the resultant EMF after armature reaction. As you see, there is an increasing effect, and we call a dramatic increase in EMF due to armature reaction. It is not clear here, but let's please refer to Turkish text book. It is not clear enough to deduce. Okay, now let's deduce or conclude. Let's conclude. In the beginning we have induced EF and then E after armature reaction E, and we have seen that E is larger, and armature reaction cause some dramatic increase in EMF under loaded case. It is not clear. You should draw carefully. Okay, ladies and gentlemen, here are there are two more operations, but they are a bit difficult to interpret. But let me say them first, and then I will show animation. Ohmic motor operation. Now, gentlemen, you have seen that armature winding has resistive and reactive components, inductive components. So it is easy to understand a lagging current. But even if there is some inductive elements, that guy can act as if it is a pure ohmic device. It is very difficult to interpret, but I assure you that it would be. I will show some animation related with this. First of all, let's draw our frames first, and then draw V1 on reference line, and then draw pure ohmic current, that is I1. Here's the phase angle, which is 0. It means pure ohmic loading, no phase difference. And then resistance times array subtracted, and then J I1 x sigma subtracted, and then the largest one J I1 x A, which is armature reaction EMF, subtracted. Those are perpendicular. Finally, you have find out EF, the position of EF. That is the angle from voltage to EF, which is pip delta. Delta is negative because you have swept in negative rotation direction. To find out where EF is, the delta is negative. It means motor operation. And then here is low TMF, which is E. And then first of all, you have induced no low TMF. After loaded case, armature reaction caused some change, and you got a resultant EMF. As you see, it is smaller after armature reaction. Armature reaction cause a decrease in EMF. In fact, there is a slight decrease. Again, this term has no d-axis component. There is no voltage axis component. This term has no voltage axis component. So in such a case we call slight. And remember, all ohmic cases are result in slight decrease. Here you see a change in d-axis that cause a strong or dramatic, that makes some dramatic or strong effect, which is dramatic increase in EMF. Finally, let me complete the topic. Capacitive motor operation. take care. A leading current. A leading current motor. Pop. I remember leading current is drawn by some capacitive elements. Even if there is no capacitance inside the machine acts as if there are some capacitive loads inside, capacitors inside. It is not real, but the result is real. Machine operates as if it is a capacitive device. Let me show you. Here's the reference line, here's the positive rotation, and then first of all draw reference vector on this V1, and then draw a leading current to find out the current position, move in positive rotation direction because phi is positive, leading, capacitive. Okay, that is the I1. And then I1 minus I1 times array subtracted. Those are parallel to each other. And then JI1 X sigma, those are perpendicular to each other. And then J I1 XA, that is the most dominant one. And finally you got EF, where EF is. The angle between reference and EF, from reference to EF, beep beep, it is delta. Delta is negative here in this case. It means motor's operation. And then here is one more term, which is low TMF, and this guy is armature reaction EMF. Initially you got this guy in magnitude, and after loaded, after the machine have some capacitive load or capacitive operation, armature reaction made an effect, and resultant EMF has a decrease, and there is a strong decrease or dramatic decrease due to armature reaction. Okay, in the beginning of motor phasers, I said when we cut the machine, we see some resistances and inductive reactances. So it is easy to understand inductive motor operation, which is a lagging current case. And then, as a second case, I said it is difficult to interpret the ohmic case. And as a third case, that was the most difficult one to interpret, because machine acts as if there are some capacitors inside. It is very difficult to interpret. And let me show one more psi from EF to current, that is psi, and perhaps somewhere here EF to current psi, and here it is psi again. Okay, now let's observe the change in animation. Okay, here in this case, machine is operated as a generator because voltage is chosen as reference, and delta load angle is positive here, you see. And then I apply there is a constant torque applied to generator, constant torque, and machine is driven at the constant speed. Speed is constant, so torque times angular speed makes constant input power. Array is neglected since it is infinitesimal, and then let's observe what is happening. When I change, that is EF, in fact, the animation is from European Tempus project, European Union, a project, Tempus project. Increase IF, field current, that causes some increased magnetic field. And then dependent voltage source here will induce much more EMF. But here, Houston, you observe a change in the magnitude of EF, induced EMF. But you observe that EMF is always such an asymptote, blue dashed line. EF is always on this blue line. Okay, here you see. And there is another thing. Current, again, cause that change. You change only field current, and there is a change in electromotive force. As a result, there is a change in load current. There is a change in phase displacement here. Ta-ta! In such a case, the current is ohmic. You see current is lagging or inductive operation. You see current is leading with respect to voltage, which is reference. Current is leading, which is capacitive current. By changing field current, you change field, you change EMF, then all the triangles, all the phasor diagrams satisfy each other. Left hand side must be equal to right hand side. So, as a result, machine will change operating mode. Let's see. Ohmic generator, inductive generator, ohmic generator, capacitive generator. Now, assume that here is a infinite bus system. I mean, the generator is supplying Turkish national grid. The current direction is wrong here. Take care. Current must be outgoing, not incoming. The generator is supplying Turkish national grid. Okay? And then I am on grid. Now, at a certain point of field current, the generator only supplies pure ohmic loads. Power factor is unity. Then, when there is excess field current, you see, machines supply much more current, but take care. Cosine component of current will be constant. Only sine term, I sine phi, will change. So, reactive power will change. So, power factor will change. Now, power factor is unity. Now, it is less than unity. Now, it is less than unity. Machine will change its operating mode by controlling field current. That was the generator's mode. In generator's mode, you can change machine's reactive status by changing field current. Here are something wrong. The equation is wrong because EF is equal to V1 plus blah blah. Here the equation belongs to motor operation. The current position belongs to motor operation, but delta is generator's operation. So animator or programmer got confused a little bit in this case, but the other things are okay. Okay, now I think here is one more animation. Let me find it. Three-phase exertion, just get sorry and okay. Is it? Again, that is generator. Okay. Now, let's conclude here. That active and reactive power change control methods will be discussed later, but in motor operation, in the beginning I said it is very difficult to interpret capacitive motor operation, but if you increase field current, that will result in some flux increase and it will change magnitude of EF. Here's the magnitude of EF. But again, here's the magnitude of EF. Again, here's the magnitude of EF. It will changes, and the triangles must satisfy the equation written here. Left hand side must be equal to right hand side. So all the vectors will cause to rotate. And then machine go under another operating mode. It would be ohmic motor, it would be capacitive motor. Please try to understand those cases. The links for this is given here in English written slides. You can examine, but it requires flash plugin, and you know it is no longer supported by browsers, but there is an emulate simulator, Ruffle simulator, flash simulator. You can simulate by using Ruffle. Okay. Choose a flash movie and then examine, animate. Okay, that's the end of today's course.